We are diving today into a paper that I think really changes how we should think about teaching robots real-world mastery. The title is FitPive $0.66, a VLA that learns from experience.
Yeah, this is a major step forward. It's moving these vision language action models, VLAs, from just being flexible demonstrators to, well, truly robust production-ready workers.
And the core breakthrough is a method they're calling RECAP.
That's right. It stands for Reinforcement Learning with Experience and Corrections via Advantage Condition Policies. It's a bit of a mouthful, but the idea is powerful.
For anyone just catching up, VLAs are amazing because you can command them with natural language, but flexibility isn't mastery. The real problem the authors are tackling here is how you take these huge models and get them to actually learn from practice from their own mistakes using RL.
And that has historically been a nightmare. Scaling reinforcement learning to these multi-billion parameter models is just, well, it's famous for instability.
So what's the fix?
The fix is this combination of the TPRS 66 sensor architecture and the RECAP method. They use offline pre-training, but then they have this really smart, iterative, fine-tuning loop that uses every piece of data it can get its hands on. Demos, the robot's own trials, and this is the key, human corrections.
And the technical lever that makes all that messy data useful is something called advantage conditioning. It's how they turn that real-world experience into a clean signal for improvement. And the results, I mean, they really are impressive.
Oh, absolutely. On these complex, long-horizon tasks, like making a proper espresso or folding all sorts of different laundry,
Yeah.
RECAP more than doubles the task throughput, so the robot gets faster and more reliable. It also roughly halves the task failure rate.
When you hear they ran the espresso task for 13 hours straight, that's not just a cute demo.
No, that's the goal right there. That's pushing VLA performance into the realm of, actual practical industrial use. That durability is the mission.
Okay, so let's unpack RECAP itself. This is this iterated loop that sort of formalizes the robot's practice. How exactly does it work? What kind of data are they mixing together here?
Right, so the structure is this very efficient, iterated offline RL process. And they realize, look, you can't just rely on one type of data. You need this heterogeneous blend. They break it into three streams.
Okay.
First, you've got your foundation, initial high-quality human demonstrations. That's your text demo. It teaches the robot the basic moves.
Right, so that's just standard imitation learning data.
Exactly. But we all know imitation learning hits a ceiling pretty fast. So the second stream is autonomous rollouts. This is the robot just trying the task on its own.
Succeeding sometimes, failing a lot.
Failing a lot, yeah. This is the experiential data. It's often very off-policy, very noisy. And then the third stream, which is maybe the most interesting part, is the corrections.
The human interventions.
Yes, expert teleoperated interventions. When the policy makes a really bad mistake, something catastrophic, an operator just jumps in, takes over the controls, and corrects the trajectory to save the trial.
That's a fascinating point. Why train on those corrections? I mean, we know expert interventions can be kind of jerky and suboptimal themselves. Doesn't that just add more noise?
It does, but it's vital. It's because of exploration. In the real world, failure can mean the robot, gets stuck in a corner or drops the portafilter. These are catastrophic states.
And it can't get out on its own.
Exactly. Interventions break the robot out of those bad states and provide a super clear signal. Okay, after that really bad state, this action, the expert's correction, leads back towards success. RECAP makes sure the whole system learns from both the successes and these critical recoveries.
So the loop takes all three data sources and cycles through three steps. First, data collection. Second, they train a value function, vTextRoot, on all the data. And third, they use that value function for what they call advantage condition training to improve the policy. It sounds like steps 2 and 3 are where the real magic is.
That's precisely it. They use that value function to basically put a quality score on every single action in that huge, messy data set. This lets the policy focus only on the good examples, no matter where they came from. A perfect demo, a lucky autonomous run, or a critical human save.
Let's pivot to the architecture then, to $0.66. For the engineers listening, what's this model built on?
So $AD66 is the latest version. It comes from $66. It's using a really big vision language model backbone, specifically Gemma 3.4b, and a training procedure they call knowledge insulation, or KI.
Knowledge insulation. Can you explain that quickly?
Sure. KI basically freezes the huge pre-trained world knowledge in the main language model. It keeps it from getting corrupted. But it separates out the job of generating the actual continuous robot actions into a specialized smaller module.
Ah, so you're keeping the brains separate from the dexterity.
That's a great way to put it. You don't want the robot forgetting how a shirt works just because it's learning a new fold. The dexterity comes from this separate 860 million parameter action expert, and it generates actions using a technique called flow matching.
Okay, we have to pause on flow matching. This feels like a really critical technical detail. Why use flow matching, and why does that choice make traditional RL algorithms like PPO so difficult to use here?
Right, this is where the innovation really shines. Flow matching is a generative technique. It models a smooth transformation from simple noise to the complex continuous action you want. It's fantastic for producing these very smooth, human-like robot motions. But it does not give you an easily tractable log likelihood for the actions it produces.
And the log likelihood is what something like PPO absolutely depends on to work.
Exactly. PPO needs that log likelihood to calculate its gradients and figure out how to update the policy. Without a stable log likelihood, which is the case for these advanced generative models, PPO just becomes unstable. It's unreliable. It just doesn't scale. This is why they had to invent a whole new way of doing things.
Enter advantage conditioning. This is the mechanism that converts that messy RL signal into something the VLA can actually understand. So how does it work, starting with that value function?
So first, they train this multitask distributional value function. Instead of predicting a single number for the expected reward, it predicts the whole distribution of possible future returns. Think of it as predicting the whole spectrum of how quickly and successfully the task might finish.
So instead of just 70% chance of success, it's more like there's a 50% chance of finishing in 30 seconds, a 20% chance in 45 seconds, and a 30% chance of failure.
That's the idea, yeah. They discretized the value space into 201 bins. This distributional approach is just much more robust, especially when you're dealing with diverse, long-horizon tasks.
Like 13 hours of making coffee.
Like 13 hours of making coffee. So once you have that value function, you calculate the advantage. The advantage just measures how much better or worse the action you took was compared to the average expected value being in that state. Positive advantage, good action, negative bad action.
And here's the secret sauce. Instead of feeding that continuous, noisy advantage value back into the model, they binarize it.
This is the core innovation. This is what makes it scalable. They take that continuous advantage and they turn it into a single input token, ILIL. This token is simply advantage positive if the action was good enough or advantage negative if it wasn't.
So you're translating all this complex continuous math into a simple language token that the large language model part of the VLA can easily process.
That is the perfect way to put it. You're turning this really hard RL optimization problem into a conditional supervised learning problem. The VLA is trained to generate the best action conditioned on seeing that advantage positive token. It learns to ignore the actions associated with advantage negative.
And what about the human corrections? How do they fit in?
They get a special rule. When an expert intervenes, they just force that indicator token to be advantage positive, no matter what the value function says. They're essentially telling the model, trust me, at this critical moment, this human action is the ground truth for how to recover.
That simplifies the learning task so much. It's just brilliant. Instead of this complex optimization, the policy is just learning to pay attention to the best data, guided by the value function's score.
It is. And it's totally compatible with flow matching, which is why it works where PPO failed. It just leverages the VLA's natural ability to handle token conditioning.
Let's get to the proof then. The results. They focused on 3 big real-world task categories, using throughput successes per hour as the main metric. I love that metric. It combines speed and success.
Me too. The first one was diverse laundry folding. 11 different types of items, but they really focused on button-up shirts for the hard metrics. It requires really fine manipulation, long horizon planning.
And the result?
RICAP more than doubled the throughput compared to the baseline policy that was just trained with supervised fine-tuning.
Doubling throughput on folding a shirt. That's the difference between a cool demo and something you could actually maybe deploy.
Exactly. Then there's the make espresso task. This one's arguably even more complex. You've got liquid handling. You have to precisely align and lock the portafilter.
The initial model really struggled with that one, right?
It did. The SFT tunes policy only succeeded about 40% of the time. RICAP boosted that success rate to over 90%. Again, throughput doubled because the robot just stopped making so many mistakes.
They also looked at box assembly, which is more of an industrial scenario.
Right, folding, labeling, stacking. And across all of those subtasks, RGCAP showed consistent, significant improvement. It just demonstrates that the learning approach generalizes across different kinds of manipulation.
And it wasn't just a one-time improvement, right? The iterative results they showed were really compelling.
That's a key point. You can see in their plots over 2 iterations of retraining, the success rate might hit 90% pretty quickly. But the throughput, the speed, keeps climbing in that second iteration. The policy is still sharpening its execution, making its moves cleaner and faster, not just more successful.
For me, though, the most convincing data point was the head-to-head comparison against other methods using the exact same data.
This is what validates their whole technical approach. They benchmarked recap against advantage-weighted regression, AWR, and of course PPO. AWR is a pretty popular offline RL method.
Yeah.
And it achieved decent success, but the policies were so much slower. The throughput was low. It suggests AWR just struggled to weed out all the hesitant, unnecessary motions.
And PPO, as we talked about.
TPO just couldn't stabilize. It completely failed in this setting with this action space. It really proves that you can't just throw a standard RL algorithm in a big VLA and expect it to work. You need a method like RCAP that's designed for these generative action models.
I also wanted to touch on that targeted failure mode experiment where they fixed the issue of the shirt collar facing down.
Yes, a perfect example of surgical error removal. They used just a tiny bit of data, a few hours of focused intervention on that one mistake, and our recap got to a 97% success rate on fixing that specific problem. It shows you can use this to hunt down and eliminate those last few annoying, costly errors.
So the takeaway is pretty clear. Our recap shows that an efficient RL loop like this is maybe the most direct path to getting production-ready robustness and speed out of these massive VLA models.
That's absolutely right. They've really bridged the gap from simple imitation learning to practical RL for VLAs.
Of course, the authors are very upfront about the system's current limitations, which point to some fascinating future work.
Like the fact that there's still a human in the loop. Exactly. The system is great, but it still relies on humans for labeling, for reward definition, for resetting the scene when things go really wrong. It's not fully autonomous yet, and the exploration is still pretty naive. It's mostly just relying on the policy's own randomness and those human interventions.
And the loop itself is still technically offline, right? You collect a batch of data, stop the robot, retrain the model, then redeploy.
Right. The next frontier would be a truly online system that's updating as the data streams in. But what Recap has achieved is so critical. They cracked the code on how to make all this messy, real-world experience useful by turning it into a crisp, binarized language token.
Which brings us to a final thought. For any of the technical teams out there developing VLAs, this paper seems to pose a really provocative question. The challenge is no longer just about generating complex actions. It's about how you can effectively convert reliable value estimates, your knowledge of what the robot should have done, into a guaranteed stable improvement in what it actually does.
It really forces you to think about data quality and value estimation as the primary bottlenecks, not policy optimization. They've given us a clear roadmap for how to achieve mastery through this kind of filtered conditional learning.
A lot to mull over as this field just keeps accelerating. This has been a fascinating deep dive into Topinal sixth sense and the power of RECAP. We definitely encourage you to explore the source material further.